Look at a raging ocean storm, or a dense forest, or a sprawling city. The physical world appears infinitely complex, but every single piece of that variety is built from a menu of roughly 100 ingredients. If you zoom all the way down to the microscopic baseline of reality, you find the atom. The atom is the smallest unit of an element that can exist. This diagram shows what happens when you group identical atoms together. When you have a pure, uniform substance made of only one specific type of atom, you have an element. We keep track of these building blocks on the periodic table. It serves as the universe's inventory list of every element we have ever discovered. Chemists use a universal shorthand to identify them. As you can see here, each element gets a 1- or 2-letter symbol. The first letter is always capitalized, and the second is always lowercase, like a capital O for oxygen or Na for sodium. Since there are only around 100 of these basic elements, the millions of distinct materials around us are the results of those single elements combining. When two or more different elements chemically bond together, they form a compound. Compounds are governed by strict ratios. In this model, exactly 2 hydrogen atoms lock onto 1 oxygen to make water. Altering that ratio by a single atom creates a different substance. Adding 1 more oxygen turns it into hydrogen peroxide, a chemical you shouldn't drink. When elements lock into these new compound structures, their physical properties change. The resulting substance possesses characteristics that are distinct from the elements that formed it. For example, take a magnetic gray metal and a yellow powder. React them together and produce a non-magnetic solid. The separated element's original traits vanish. Once chemically bonded, the compound cannot be separated back into its original elements by physical means like filtering or boiling. You have to break the chemical bonds. Chemists use naming rules to categorize these newly formed compounds. If a compound contains a metal, the metal's name always goes first. The nonmetal alters its suffix to "ide," forming sodium chloride. If oxygen is present, it becomes ate. Copper, sulfur, and oxygen make copper sulfate. To break these named bonds and separate the compound back into its base elements, you have to force a new chemical reaction. These naming rules act as a direct code. By simply reading the name, a chemist knows exactly what a substance is made of and how it is bound together. A chemical reaction is the event that creates or breaks these compounds. It always forms 1 or more new substances and usually involves a detectable energy change, like the release of heat or light. To document the before and after of these events, scientists start with word equations. They write the names of the reactants you start with, an arrow, and the products you end up with. Symbol equations track specific elements. Here, methane and oxygen form carbon dioxide and water. Bracketed state symbols indicate if substances are solid, liquid, gas, or aqueous. Chemistry is a closed system. The law of conservation of mass dictates that no atoms are ever lost or magically created during a reaction. Currently, this scale shows an unbalanced equation. Atoms on the left don't match the right. To fix this, we balance the equation. By adding a 2 in front of the oxygen and water, the scale levels out perfectly. Reactant mass now equals product mass. An equation reflects the laws of physics, proving that every single atom in a reaction is accounted for. Beneath those shifting atoms, an even smaller, invisible exchange is happening. Half equations and ionic equations zoom in past the whole atom to track the behavior of electrons. These advanced models track the specific transfer and sharing of tiny, negatively charged particles. Those movements are the physical drivers of chemical bonds. Chemical equations aren't just textbook problems. They are the accounting system of the universe. They allow us to read, predict, and manipulate the physical materials around us.